Not this one. Actually, no, you gotta like get that from 2020. During break. Before the search,
Okay, good morning everyone. Good morning. So homework I'm going to be posting tonight. It will be due next week Tuesday. Okay, so you'll have enough time for it. I just want to space out the work because you had an exam on Monday last week. You have a quiz due on Tuesday this week. I don't want to have things due on Friday this week. Okay, it will be due next week Tuesday. And my expectation is that I want to have only 2 more homework sets. So one which will be due next week Tuesday, and then one last one which will be due at the end of the semester. Okay, so just 2 more, but it will be pretty exhaustive in terms of the problems that we cover. Okay. All right. I'm grading your exams, in the process of grading them, so thank you for being patient. I hope to have them by the end of this week, for sure. Yeah. And hopefully by next Monday all your grades will be posted. Alright, so here for today we are going to start looking at 3-dimensional combined loading problems. I'm going to start with the first one, the problem. Alright. Okay, so in this problem I have a pipe which is fixed to the wall. Okay, it's drawn in the following manner. So here's a pipe whose back end is fixed to the wall, so it's some kind of a shaft in some sense. This is a solid pipe or a solid shaft. The radius is given as 10 millimeters. Here are the forces acting on this. First of all, there is a torque on the free end of the shaft or pipe. This torque has a magnitude of 200 Newton meters. Then there are 2 forces which are acting on the free end, one of them pointing vertically down, the other onto the side of the face. So if I have these 2 as my axes, and then I have the axis of symmetry of the pipe itself, which is coming out of the page, out into the page. There is one force which is acting vertically down, and then this has a magnitude of 200 newtons. Then there is another force which is acting onto the side of magnitude 300 newtons. Okay. Length of this is 1 meter, the total length. And I'm going to draw a set of parallel axes back on the fixed face. So this is the back end here. And I'm going to choose 3 points on here. Okay, one is the topmost point, which I'm going to call as point A. So this is point A. Then I have the center C. Okay. Then on the other side I have this point, which I'm going to call as the point B. Length of this pipe is 1 meter. And the problem says the following. Given the radius of this pipe as 10 millimeters, the arc is 10 mm. Okay. Obtain the stress matrices at points A, B, and C. Obtain sigma A, sigma B, and sigma C. Okay, so these are all matrices, which means that they will have a collection of the normal stresses along the diagonal, the shear stresses will be along the off diagonal. Okay, so we have to come up with what are these values for the stresses. Okay, and the back end is fixed, so this is a fixed end. what are the steps involved in this solution. In some sense, there is no shear force and bending moment diagrams involved, but in another sense, it is still included, in the calculations that we do. So this problem is, in a sense, a straightforward one because it already tells me, okay, these are all my points of interest. Okay, point A, point B, and point C. Okay, I don't need to focus on any other point. So what I have to do first of all in any problem is I have to do the statics, which means I have to find the support reactions at the fixed end. So I have to draw the free body diagram of the shaft, mark all the unknown forces and the unknown moments and the unknown torques, and then sum it up and find them out. So let's do that. So free body diagram. Take this entire beast, rip it out of the fixed end and draw it out. Okay, so here is the entire thing. Forces and so on acting on it. So here are the forces. I'm just redrawing whatever these forces are. One this way. This way. And then the torque. The torque is applied such that the thumb is pointing away from the free end of the shaft. Right? So the direction of the torque, if you like, is essentially pointing this way. So if I call this as T, this is the direction of the torque. The sense of the torque is counterclockwise. Alright, so this is 200 newtons, 300 newtons. This is the sense of the torque. It is not necessary to show both of these things. Either you show this or you show that, and then you write the value of the torque. Okay, it's completely fine whether I just show this, but the double arrow indicates that it's a torque or it's a rotation of some kind. Okay? Then, before I start marking the support reactions and so on, I set up a coordinate frame at the fixed end of the shaft. So here is where you have freedom to be creative. You can call the vertical axis as the z-axis, the horizontal axis as the y and the x-axis. That's completely up to you. In some problems, you may have a coordinate frame given to you, which makes your job easier. In this problem, there is nothing given to me, so I'm going to choose my own frame. Okay? The vertical axis, I usually call it as the y-axis. Then I'm going to have an axis that is through the axis of symmetry of the shaft. I'm going to call it as the x-axis, so coming out here is my x-axis, which means that my z-axis is going to be given by the right-hand rule. The right-hand rule meaning that if I align my fingers with the x-axis and I curl my fingers towards the y-axis, the z-axis is pointed along the direction of the 300 Newton force. Okay? So if I draw that out, this is going to be my z-axis. And I also mark my points of interest. I don't label them yet, but there's one there, there's one. Alright, does my labeling convention make sense to everybody? Any questions on the axis system so far? Choose two directions. You're free to choose it. The third has to come from the right hand. Yes, sir.
So is point B on the z-axis?
Point B is absolutely on the z-axis, on the other side of the positive z-axis. Right. So maybe for reference we can, this is z, this is x, and this is y. So B is on the z-axis. Okay? But that coordinate system was not given to me to begin with, you see. So they make me think, okay, what's the best coordinate system for it? Anything that you're convenient with. And then I start marking all the reaction forces and reaction moments at the fixed end. Because it's a fixed end, how many reaction forces are going to be there? 3. one along each axis. How do you draw the positive reaction forces? You just point them along the positive axis directions, that's all. Okay? So my first reaction force is going to be a normal force, okay, coming out of the cross section at the end. Then my second reaction force is going to be along the y-axis. I'm going to call it as T suffix y, or a V suffix y, I'm sorry. Okay, those are my reaction forces, and I'm going to have one more along the z-axis. Makes complete sense to point it along the positive z. Call it as V suffix z. Those are my reaction forces. I'm going to have 3 reaction moments, out of which one is a torque. Okay, so watch this. I'm going to have a reaction torque at the fixed end of the shaft, like we have been doing for torsion problems. Okay, so that's going to be double arrows here. I'm going to call it as T suffix x. Okay, so if you want, you can also draw the curly arrow, signifying that, but there are too many arrows and makes life very miserable. Then I'm going to have one more moment, 2 moments now, 2 bending moments. This is a torque. I'm going to have 2 bending moments, one about the y-axis, one about the z-axis. Common sense tells me that I will choose my bending moment direction such that if I clutch, for example, the y-axis, I curl my fingers, the direction of the bending moment is along the positive y-axis. I don't know if this is true or not. Okay? So I'm just going to draw it out here, extend this a little bit. Once again, what I'm doing is I'm seeing this large pole, which is the y-axis. Take the fingers of my right hand and I clutch it such that my thumb is pointing along the positive y direction. Okay? Do the same thing for the z-axis as well. I'm just going to extend this a little bit. Yes?
Professor, if that TX is going out, wouldn't that like torque be the opposite direction?
Say that again.
Like, cause the torque at X is going out that way, so wouldn't be the rotation is the other way, right? It would be that way.
I don't know it. No. These are all things that I'm marking without doing the force balance and the moment balance. So I am just assuming certain directionalities. Yeah? As you said, what you were asking?
Yeah.
No, I want to clarify. So are you asking why I chose it to be this way?
No, this way is right, I get it. But I'm saying for the X, for
Uh-huh.
the X-axis, shouldn't it be the other way, because the X is pointing outwards. So shouldn't it be the other way?
No, my arrow was drawn this way.
Oh, okay.
Yes,
I just
it's perspective. That's why I like these double arrows. There is no ambiguity there.
Okay.
Yeah. So you had a question.
Oh, I was just gonna try to clarify.
Oh, trying to clarify. Okay. Is everything good now?
Yeah.
Okay. So this is, I'm going to call this as M suffix Y. Okay, these are all reaction moments. That's why 3D problems are tricky, because there are 6 of these creatures. You mess up on one of them, everything is gone. Your entire stress matrix is ridiculous. Okay, so be careful. Once again, the double arrows. Just use the double arrows if you are not comfortable looking at the sense that I have drawn. It's difficult to convey a sense by a planar picture drawn on 3 dimensions. So this is M, Z. So Mx, My, and Mx, My, and Mg, and Tx are my reaction moments. Where Tx is the reaction torque. Which means that is going to cause shear stresses on the cross section. Then I'm going to have My and Mz, which are bending moments. Which will cause bending stresses. Bending stresses are nothing but an addition or a subtraction onto the normal stresses, right? They're always going to be along the axis. So this is going to cause normal or bending stress. Then I'm going to have 3 reaction forces. I'm just listing all these things out, and I'm doing this elaborately for this one particular problem. Next class I won't be doing this. Vx, I'm sorry, Vy let's call this as nx because it's pointed along the x-axis. Okay? So nx, Vy, Vc, these are reactions. The forces. Okay? Nx is going to contribute to average normal stress. Vy and Vz will contribute to transverse shear stresses. And we have one hell of a job to calculate all of these things. Alright. It's an interesting problem. This is real life problems. And you have a pipe. This pipe is being acted upon by so many forces. Somebody's coming there, some kid is coming there trying to break this creature out. Okay, what are the stresses caused on the pipe? I need to design it in such a way that my factor of safety accounts for all of these kinds of loadings. Alright. So I'm not going to draw the figure again, but maybe I need that figure down here. So maybe I need that for the moment. So I'll pull that down in a minute. But force balance is fairly easy. You can just visually recognize that Vy is going to be equal to 200 newtons, Vc is going to be equal to minus 300, and Nx is equal to 0. But we will still do this carefully. The sum of all the forces in the x direction. There are no other applied forces in the x direction, so Nx is 0. Forces in y. Forces pointing up are taken as positive, so what are my forces? Minus 200 plus Vy. Vy is equal to 200 newtons. In an exam, you don't need to keep writing each of these steps. If you just see this guy is 200, just write it and call it a day. You have better things to do. Okay? Forces in a z direction. But it doesn't hurt to be careful. Okay? Doing all these things is being careful. So this is plus 300. Plus Vz is equal to 0, or Vz is minus 3. Okay. Then comes the more sticky thing, moments. Okay? When you do moments, the easiest moment to do moments calculation to do is about the x-axis, because there are only two things there. There's a torque applied, there's a reaction torque. Nothing else to worry about. The forces 200 newtons and 300 newtons, they have lines of action which pass through the x-axis, so they don't contribute to any moments about the x-axis. Okay, so we don't need to worry about them. The sum of moments about the x-axis at the fixed end is 0. And if you want sign convention, positive moments directed along the positive axis. And from the fixed end, if I set up a view, the torque Tx is positive. And the applied torque is going to be negative because I'm looking at it from the fixed end, like you've done for many torsion problems. Okay? So this is Tx minus 200 is 0. Is there any ambiguity on this one? Everybody on the same page? I'm setting up the view at the fixed end. Okay? Everybody good on this? Okay. Now comes the more challenging issue. I want to do this on two separate panels. Moment about the y-axis. Okay? So I'm going to draw the figure once again. You don't need to draw this, you already have your figure. And you can draw it for simplicity. about the y-axis along at the fixed end is 0. Okay, so this is the y-axis. Sum of moments. Positive sign convention. Moments pointed along the positive y-axis are positive. This is done at the fixed end. If I do this, what are the contributions? Or who are the contributors? Let's start whittling this down one by one. Okay? This creature is out of my books because the rotation caused by the torque is about the x-axis. Then I start looking at this force, 200 Newton force. It's a force parallel to the y-axis. Okay, question.
Yeah, based on how you drew 2 sub x, wouldn't 2 sub x be negative 200?
Why is that?
It's the same confusion I have.
Okay, so
Just assume it's counterclockwise.
yeah, so. So what I should have drawn, it's to me it looks good from here, it still looks good from here. Okay. So you would prefer that I had drawn it this way. Does this make sense?
Yeah, that's.
All of you happy? All right, let's move on. Okay, all I had done was I had drawn the arrow a little deeper.
Yeah, I know.
Okay.
Okay.
I figured that out.
All right. That's just a fair point. Okay. I don't want to have any ambiguity because, as I said, you make a mistake in one of these silly fellows, your entire problem is derailed. Yes.
Are you getting rid of that 200 because it's at
I am going to do it. Yes.
because it's at the other end?
Huh?
Wasn't that the same thing?
It is the same thing, yeah, but some people had they think they thought it was in a different sense. Completely fine. We are all good to go. Okay? It's all the same thing. No confusion. No confusion. Use the double arrows. When in doubt, double arrows. Okay? So first things first, why did I get rid of this? Is because this is a torque about the x-axis. So it's not going to contribute to the moment about the y direction. Was that what you were asking for?
Yeah, I was asking about the 200 because it's at the other end, right?
Say this louder, please.
Just that T.
We're just getting rid of that because it's at the other end.
I'm just getting rid of it. Right. I'm drawing all these applied forces and applied torques and so on. And one by one I'm getting rid of it. Okay? 200 Newton force is a force parallel to the y-axis. If I try to open a door by applying a force parallel to the axis of the hinge, I'm not going anywhere. I'm just going to come with a dislocated shoulder. So this is done. Makes sense to everybody? A force parallel to an axis cannot cause a rotation about that axis. It has to cause a rotation about an axis perpendicular. So this guy is the culprit, 300 newtons. Right hand rule. Fingers of my right hand aligned with the force of 300 newtons. My palm is facing the y-axis. You see there? The y-axis. I curl my fingers. This 300 Newton force multiplied by a distance of 1 meter is also going to cause a rotation about the positive y-axis. Once again, my fingers are coming out of the board, okay, aligned with the direction of the actual force, 300 newtons. My palm is facing the y-axis. I curl my fingers. My thumb is pointing in the positive y direction because I am multiplying 300 newtons by a distance of 1 meter to cause a rotation about the y-axis. Okay, so this is going to be 300 times 1, that's one contribution. So I'm done with that. And you can see how messy this problem will get if I start putting forces at different angles. You have to resolve all of them into components, statics, and then you have to do the support reactions, and you're going to have that exclusive experience in your next homework. All right.
Yes.
I'm just being a prick. That's okay. So this guy is just directly going to be thrown into the hoop. Is equal to 0. So I instantly realized that MY is negative 300. Do the same thing for the z-axis. Okay, moments about the z-axis. Do you guys have a question?
Over there, is it supposed to be 200 times more or?
This is 300 times. So 300. Looks like a 200, it's a 300. Okay. The moment about the z-axis, where's my z-axis? So this is my positive convention. Once again, you don't need to draw the entire figure. I'm just doing it for this one particular problem, so please bear with me. Okay, so here is my mz. Then I have my forces, I have my torques and so on. Newton, 200 Newton, distance of 1 meter. Okay, watch this. That's the distance that I'm interested in. Okay. Now I start eliminating each of these creatures. 200 Newton meter torque, obviously we've taken care of that fellow. Then the 300 Newton force is parallel to the z-axis, so it's not going to cause a rotation as well. So this is also gone. Everybody with me so far? Forces parallel to an axis cannot cause a rotation about that axis. Okay? Which leaves me with this 200 Newton force. Slightly tricky to use the right hand rule because I can't contort my hands in that manner, but I hope you get the idea. My fingers are pointing vertically down, okay, along the direction of the force. My palm is facing the z-axis. If I curl my fingers, multiplying the 200 Newton force by a distance of 1 meter, I will get a moment in the positive z direction. Okay? That's what is going to end up the case. So I have, if I sum up all the moments caused out due to all of these guys, I'm taking care of this one. So mz is minus 2. All right. Yes, sir.
Can you explain one more time, I'm sorry, why you got rid of the applied torque for the moments about y and z?
Oh yeah, so the direction of the torque is about the x-axis. But I'm summing moments about the y or the z-axis, right? So this is not going to influence my moments in that direction. Yeah. And right hand rule for this guy, 200 newtons, right hand rule. Fingers align with the force. My palm faces the z-axis. Curl my fingers. Comes out of the page, which is my positive z-axis. And all this is based on the axis system that we created together. I could label these axes as completely different, choose two directions, call the third direction using the right hand rule. The subscript should be changing on each of them. Okay? Alright, now we come to the remedial part of the problem. I'm going to push the board up. So you saw that we had some forces and moments that were negative and so on, right? So now I'm going to set that straight because I have to find out what these forces and moments, what kind of stresses that they cause. So now I'm going to redraw the free body diagram. Wherever I got a negative value for the moment, I'm going to change the direction and write it as a positive. Okay? And for you, you don't need to keep drawing multiple figures, you can just take care of it in the main figure itself. Y, X, and Z. And it's not necessary to show the applied forces and so on because we already accounted for it. So here are the forces that I end up having. For me, Nx was 0, so I don't even bother about it. Vy was 200 newtons, positive y direction, so Vy. Newtons. Vz was around minus 300, so I have to switch the direction of Vz. Please notice I have now said that Vz is plus 300 newtons, pointing in the opposite direction to what I assumed it to be. Okay. Likewise, I have the torque. It's about the x-axis, positive x-axis. So I want to make sure I'm not confusing anybody. I will just use the arrow that I have there. Ex 200 newtons. Okay. Then My and Mz. I had obtained My to be negative, and previously it was pointing along the positive y, so now it's going to be along the negative y. My is going to be plus 300 newtons. Mz was taken to be along the positive z-axis to begin with. I got a negative sign, so it's going to be pointing along the negative z. This is Mz. And the way I have drawn Mz, it is now positive 200 newtons. Points of interest. A, B, and C. Is everybody on the same page? Are you all able to see the figure that I've drawn clearly? People in the back? All of you following me? Okay. Any questions so far? Alright. So now I'm going to set up a view. So here is where I draw the long-necked creature. I'm going to take the entire three-dimensional cross-section, flip it towards you. Okay, so now I'm going to draw it as a two-dimensional thing. So at the view, okay, so here is now a two-dimensional figure, no longer three-dimensional, because the x-axis is coming out of the page. Y-axis. The z-axis, if I take this creature and I flip it towards you, what's the direction of the z-axis? The z-axis is going to be pointing to my right. And then the x-axis obviously is going to be coming out of the page. Then the direction of the torque. The direction of the torque is counterclockwise with respect to the x-axis because of what we have drawn there. So Newton meters. This is Tx. Extend these lines. Then the shear force along the y-axis is along the positive y-axis, so I can just point it out that way. Newtons. And then Vz is along the negative z-axis, so I have to mark it out in that direction. 300 newtons. Then I have the couple moments, or the bending moments. I've taken care of the torque. Then there's going to be one about the y-axis, then about the z-axis. The y-axis moment is about the negative y. So extend this line. And this was 300 Newton meters. And then about the z-axis, it was pointing along the negative z-axis. Points of interest. Centroid C, easy point. The point A is where the y-axis intersects the cross-section, the circumferential cross-section. So that is point A for me. Then I have point B. which was along the negative z-axis, so point P is going to be sitting here. Everybody good to go on this? So the steps that I would like you to show me, when you're solving these problems is a 3D view with the support reactions, calculation of all the support reactions. You can skip all these intermediate figures and so on. I need to see this figure here. Okay, so that's the second figure you need to show me. First is the free body diagram. And the third is the 3D view condensed into a 2D figure. So this is the third figure that you need to show. 3 figures, list of calculations. We should be good to go. Okay. Let us choose point A. Let me look at the torque of 200 Newton meters, which is acting at the point A. So I'm going to have tau A due to the torque. This is the x. This is dz. This is dy. Y. Okay, so due to the torque, Tx, this is your typical formula, T times C divided by J, which is 200. C is the radius, which is given to us 10. J, polar moment of inertia, pi by 2, r to the power 4. Crunch the numbers. It's around 127.3 megapascals. Okay, to do the calculations. But this is not the way I want to write it, right? Because this doesn't tell me anything about the directionality of the shear stress. So I go back to my figure here, my two-dimensional viewpoint, and I see what's the direction of the shear stress at point A. Pointing this way. Then I start putting the subscripts. So tau A due to Tx, I calculated the value 127 megapascals or something. What are the subscripts? The second subscript is typically the direction of the area normal, right? So in this case, what is the direction of the area normal? It is the x-axis. So that's my subscript there, the second subscript. The first subscript is the direction of the shear stress itself, which is along the z-axis. So this is going to be tau A due to the torque Tx and pointing along the zx direction. Everybody clear on this? This is basic calculation, you've done this many times. Calculate the number. Second subscript, even if I'm going to do just one point, I want to do this very carefully. Second subscript is always the direction of the area normal. The first subscript is the direction of the actual stress. In this case, the shear stress is pointing along the z direction. If I had a bending stress, both of the subscripts would be the same, because the direction of the area normal and the direction of the bending stress is the same. Alright, so that's done for the point A. Now, my question to all of you. If I consider the force Vy, what is the neutral axis for the force Vy? Is it the y-axis or the z-axis? It is the z-axis, right? The axis that is perpendicular to the shear force is the neutral axis for that particular shear force. Which means that the point A, according to the shear force 200 newtons, is at the edge of the circumference. Which means there is going to be no shear stress contribution at the point A due to this force Vy. I want to walk you through these steps one more time. So for force Vy, neutral axis is the z-axis, which means whatever points are on the neutral axis will see the maximum shear stress. Point A is on the outer side of the circumference for the force Vy. Any point at the edge of the cross section, considering the direction of the neutral axis, considering the direction of the shear force. There will be no contributions from the transverse shear stress. Okay, so which means that tau transverse due to Vy is 0 at the point A. Am I making sense to everybody? Or if you want, you can also think of it this way. So tau transverse at the point A due to the force Vy is Vq by It, right? So this is going to be Vy Q by I neutral axis times T tau. To calculate Q, what do I have to do? I either have to look at all the area below the point A or all the area above the point A. What's the area above the point A? There is nothing. So which means Q is 0 for me in this particular calculation, which is why the shear stress is 0. Okay, yes sir.
Could you just explain again why the z-axis is the neutral axis?
Why is it the neutral axis is, so there's a long and a short explanation. You consider the bending axis. If you consider a bending stress or bending moment, the axis of the moment is the neutral axis for that bending moment. And the axis that is perpendicular to the shear force is considered to be the neutral axis for that particular shear force. Because you see, precisely for this particular reason, if I calculated the value of the shear stress at the point A based upon this, I get 0. If I calculate it at this point, I will also end up getting 0. And the value of the shear stress is going to be the largest at that axis. And so that will be the neutral axis. So this is a reverse argument in some sense. So I can start off by saying, okay, hey, is this the neutral axis or is that the neutral axis? Calculate the shear stress at A, calculate the shear stress here, calculate the shear stress here. This will give you the maximum value. That's the neutral axis. Okay. VZ is this question.
Can you explain what's the difference, like, what's the relationship between the shear stress at point A due to Tx and then the transverse that we just calculated?
Oh yes, yes. So here is the deal, right? So this is a problem where there are combined loads acting. Right? I have a torque, I have a shear force, couple of shear forces, I have bending moments and so on. What we are trying to do is we are choosing a point, some point of interest. Let's say that somebody did a failure analysis and figured out, hey, this is the point where the failure is going to occur. The cracks are going to start propagating from that point. I want to see what is the net stress at that point due to all of these loads acting. So since we are doing linear elastic materials, we can use linear superposition. That is, I look at the effect of the torque, that causes a shear stress. I look at the effect of this force here, that causes nothing. I look at the effect of this force here. For this force, then not that force, but for this force, the point A is in the neutral axis, which means that the maximum shear stress is going to be there, due to that particular force. And likewise, piece by piece, we look at each and every element that acts on that point.
So you're evaluating the shear stress caused by the applied torques and the other.
And the other two forces. Right, so we have taken care of one of them. So we call that as that. Then this is B. I need to do the same thing for BZ, 300 newtons. Okay, so I'll push the board up. Can I push this particular board up for everybody? Okay, so a couple more calculations. Alright, so here is what I have. VZ is what I need to take a look at. So the shear stress at the point A due to VZ, write the formula VQ by IT. Direction of the neutral axis The longer story is, I did not do the derivation for the shear stress calculations, right? So which is why all these details are kind of subsumed into one formula. But that derivation is kind of a detraction. So take it as a matter of faith that if I have a shear force, the axis perpendicular to that is a neutral axis. Okay? So for me, the neutral axis is going to be the y-axis for this one. Okay, so this is going to be evaluated about the y-axis. Yes, sir?
Why couldn't the neutral axis